All right. Oh, why is it? Uh, why? Oh, I think I need to. Oh, no. Okay, that works. Yeah. What exactly is it done? Okay, for some reason it doesn't stay. Do we have to stick it somewhere? Okay. For some reason it stays until here, and if I bring it down, I have to write today, so I want it to be done. There's, I think, some slots where it stops. Anyways, welcome back everyone. This is lecture 4, and in today's lecture we will introduce artificial neural networks, and we'll start talking about the basic building blocks of neural networks. And for some reason this room is suffocating me. Is that like for everyone? Plus we have masks on. Yeah, I know we had a CS1 lab here like the last 2 hours, and like people were complaining about this room. I even dropped in an email telling them to change the room, but it seems it's not possible. So yeah, can we open that? Yeah. Okay, that might help. Okay, so what I decided to do was, I know that we'll have a lot of papers going forward that we'll be reading, and we'll have like a lot of research that we'll be looking at. But I decided to go and like actually understand the basic building block of an artificial neural network. That's the perceptron. Because if you understand that, then that will be pretty easy to like translate to actual more complex neural networks. Right. So that's the plan for today. And that's why I don't have a lot in lecture 4, because I'm going to use these slides just write down, and I'm going to post the slides as well where I have like my written stuff. Plus, regardless, I wanted to go over this paper because this is important, and this is important from the perspective of like when you'll be doing your homeworks. So that means when you'll be implementing your project. This paper specifically talks about how we can improve performance. Right, so we'll go over that as well if time permits. If not, I'm going to like still go over that on Friday. So let's actually begin. And I have slides here. Let me. I know this WebEx thing might make me, but let's try this. If not, then I'll just like not do it in this slideshow mode. So the first thing that I want to talk about was the motivation behind artificial networks. So the fundamental motivation actually comes from our brain, right? So there are these neurons, like the motivation comes from biology actually. So the way the human brain works is that we have these interconnected neurons that are actually exchanging information, and that's how we are making decisions. That's how information is flowing in our brain, and that's how, like fundamentally, that's how a human brain works, right? So this key idea is the core, I would say, building block of an artificial neural network. But now the way we implement them and the way we use them in today's world, in today's applications, it's quite different. It has its own differences from this like this biological inspiration to start from. But still, you can see that these are like these neurons, and then these are these like interconnected. Okay, I figured this doesn't work when it's in like this mode, but regardless, you can tell what I mean. So there is this neuron that's like a node, and then there are these connections which may be like vertices in a graph, right? So it's similar to that. So let's actually begin with what are actually neural networks. Neural networks are also known as artificial neural networks, or ANNs, right? And they are a subset of machine learning right now, and at the very heart of deep learning algorithms. So we're going to see what this deep learning is, why this is so relevant in today's scenario, and high level idea being that we have so much data that if we are using the traditional machine learning algorithms, we might not be able to extract all the information out there. And so high level, that's where deep learning comes in, and that's what we'll be focusing on throughout the rest of the semester. Okay. Now, as I said, their name and structure is inspired by the human brain trying to mimic how biological neurons are interconnected and how they exchange information. And of course, like ANS or artificial neural networks are comprised of a node layer, that's an input, and then hidden layers, and then an output layer. Do not worry about these terms if you're not familiar with them. I'm going to like cover each and every. Okay. I think I should have done something to stop the sound, but that's okay. Okay. All right. So that's the basic definition of an artificial neural network. Yeah. So moving on to the actual structure of any like typical neural network, and let me move on to the next slide. Okay. All right. So this is what a typical neural network looks like. So we have an input layer, which is like, think about your data. So the input layer is mostly the data that you read in, and then these are the hidden layers, right? So the hidden layers actually do some computation, and then eventually you have the output layer that could be like, what is your estimation about some target variable, right? So those are the estimated values. Now you're seeing that this is a more generic kind of a picture wherein we are not bothered about like what the input layer should be. We're not bothered about how many hidden layers should be and what is the output, because this is like the most generic sort of representation of a neural network, right? So we will definitely talk about each one of those aspects. But this here, I just wanted to kind of show you the important thing to like notice here are these connections. Like, look at all these connections, these like arrows. For some reason, my cursor doesn't work in my slideshow mode. So just like notice these connections from the input. So if this was your data that's coming in, right? And then you are like combining your data at every node, and then you're getting like this wide range of inputs, right? And so that's what I talked about when I started introducing artificial neural networks, that it gives you another like high level non-linearity to be modeled in some ways, right? Because just notice what's happening. Like, and of course, this is the intuition. There is like no mathematical proof to say that, and that's something that we're going to look at in the lectures that are coming up and in today's lecture as well. But this is just like to kind of give you an idea of how we can model like really complex functions, right? Because there is an underlying function that I'm after. That's why I'm estimating some value, right? And so I can really model complex things here. All right, so let me begin with something. So this is something that we haven't seen before. This kind of a structure is not something that we usually get to see. And this is known as a computational graph, right? Which is kind of the basic structure of like representing a deep neural network, right? And we are going to begin with understanding how this computational graph works and why this is relevant in understanding when we model our data. Okay, so let's actually begin with that. So the first thing I'm going to look at is what are computational graphs. So it's just like another way of representing your data and your computations and your output and the relationship between them. So it just like makes it more convenient, so to say. Okay, so originally, if you think about the logistic regression computation that we did, right? I can express that in like in this computational graph form. So let's start with that, because all of us are like on the same page as far as logistic regression is concerned. You already implemented that, so you know the in and out of it. And so let's try to like translate that to a computational graph. Okay. So let's assume I have like these three inputs coming in. Okay, so here is the issue. I hope this works, otherwise I'll have to. By the way, so whenever I'm talking about inputs, that's my data, right? So let's say I have like three features. So x1, x2, x3. Sorry for the bad handwriting. I'll like keep talking through that. For some reason, the pen is different than a pen on paper. So yeah. Anyways, so yeah, so when when I have this input, I wanted to combine it. So we have the linear model, right? And so whenever I'm combining it and doing any kind of computation, I usually have a node, right? So that node is essentially going to combine it. So remember what we were doing, and I'm like calling it Z. So Z is W transpose X plus B. Yeah, so this is what we were doing in my logistic regression. Everybody's okay with that, right? And then there was another computation, which was the sigmoid. So once I have the linear input signal, and then I passed it through the sigmoid because I wanted to constrain the output to 0, 1, because I was predicting the probabilities, right? So I'm calling it activation, and I'm denoting it by an A, right? So A is sigma, that is for the sigmoid, right? And then just put the linear signal through that. Right? And then eventually, like once you're done, so both these steps happen within this node. Both the steps happen within this node. And then I get some output, right? So I define it loss, which is nothing but a function of my A activation and Y. So activation is that Y hat. I just removed Y hat here because you'll see when we go to the neural networks, the notation becomes like tricky. So like keeping track of the hat is the worst thing ever. You'll see. So that's why I just like replaced it with an A, right? So this is what a typical, I would say, computational graph looks like. And just keep in mind that these computational graphs are for one example, for one data. So this is like, let's say for the IS example. So you have definitely more data coming in, and you now understand that because you, right? So for one point, and why am I mentioning like that this is for one data point? Because that's why we had the vectorized notation, remember, where we took the entire data and then we saw that there wasn't much to be done, but still it's good to keep in mind that this is what's happening. Okay, questions, doubts, anything about this? This is straightforward, right? I just like translated my logistic regression to this. That's all I did. Okay, so now the fundamental difference is going to happen in like a neural network basic model, like anything, like the fundamental difference will be something like this. And I'm going to show you here itself. Let's say I'll have like these x1, x2, x3, right? These inputs. And then I'll have these nodes. And I can have like more than one node, right? And I can have like more than like, so here I just had one single computation, but I can do multiple computations, like depending on the different combinations of these inputs, right? So the first thing that you should notice is that I'm going to combine these like differently. And why would these be different? I'm coming to that. So first of all, this is here, okay, this one, and here, and what is left? And okay, this one here. So like you got the idea, right? Every input is connected to every node, right? And then in every node here, I will have a similar computation. So 2 steps. I will be calculating my Z and my A, but at every node, right? So when I do that, right, and then I'll have like another set of nodes. So most likely, like let's say I wanted one output only. And of course, we'll cover all of that, like when do we need, how many nodes and all of that. So don't worry about it, but just focus on the computation, like what's happening. So there is going to be some output from these nodes that I can combine here, right? And then I can get my loss. Okay, so what has changed really here? What are the things that have changed? So of course, I'll have like a Z-like calculation here and A-like calculation here, like in the first set of nodes. Okay, you cannot see my cursor, right, when I'm saying this. So basically, I'm talking about the 3 nodes, right? So at the point where there are those 3 nodes, I'll have some Z and A calculations, right? And then when I come to this particular node, I'll have another set of Z and A calculations. Okay, so that's the fundamental idea, and I'm going to get like L, that is going to be my final loss, right? Now, the way I'm going to denote these Z's and A's, because they'll keep appearing. Now imagine like I have a more like a deeper network with more nodes, right? So I need some way to denote how this Z and this A is different from the other Z and A. So that's what I'm going to begin doing. So this is going to be denoted by Z1, and this is like square bracket 1, and this is Z2, A2. Now, where is this 1 and 2 coming from? Well, it's coming from the definition of input, hidden layers, and the output layer. So let me first like define everything. If we go back to the previous slide here, so you can see this is the input layer. So these are my x's, right? X1, X2, and so on, right? So this is my input layer. And this is not counted as one of the layers of my network. So when I talk about my network, my layers will be counted from the hidden network, right? So this is my first layer, this is my second layer, third, and this is fourth. And this fourth one is also known as the output. So in general, if I'm denoting my like layers with like 1, 2, and so on up to L, L is usually my output layer. Okay? And my input layer is not considered as a part of the like the network. It's just the input, it's just the data. Right? So that's what I'm going to follow throughout. So let's go back to what we said here. So I have my Z1 and my A1, right? And what is going to be my Z1 here? This was like pretty simple. Z was like W transpose X plus B. Right? So let's like carefully look at what's happening. Let's focus on X1, for example. Right? So my X, so I will be having, so what exactly were we doing here? So we had like some weights to be actually estimated, right? That was the whole point. Weights and maybe a bias. Let's like forget the bias for the time being. So there were some weights, right? Now here what's happening here, there is going to be a weight from input 1 to, let's say this is node 1, right? So W1. And then there is going to be an input from 1 to node 2, so W12, and then W13. So this is just for one input X1. And similarly, I'm going to have like an input for X2, like all those weights, and then X3. Right? So depending on my input dimensions, right, and depending on my number of nodes or where I do my computation, right, I will have this matrix of weights now. Right? So this is no more like a single vector of weights that we were talking about in my logistic regression here, right? But it's like a whole vector of weights. Sorry, now it's like a matrix of weights, sorry. Right? So like the way we denote this, like when I'm going to do Z1 is going to be, and this is like uppercase W at layer 1. This denotes the matrix that's coming in, right? Times X, and this X is like my input X, right? Plus the bias B. This is how my Z1 will be computed. Okay. Now A1 will be still the same, right? It's just like the sigma of this Z1. Right, and there is no subscript 1. Let's like remove the subscript. So let's keep the superscript for like which layer I'm going into. Let's remove the subscript. Let's have the square bracket and the superscript like at the top. Okay. So similar to that, I'll have like some Z2 and A2. So Z2 is going to be these weights now, right? Times X, which in this case is going to be my A's from the previous layer. Just take a second, like if this, I know this is overwhelming, which is why I decided like, let's take today's 2 hours to just understand what's happening, right? So here I need to do my Z2 computation on the second node, right? So let me write it down. So Z's will always be like doing this linear combination. Just think about it. That's what it's doing. That's all. Okay. I'm sorry about this. I have like somehow this habit of writing subscript. Okay. So Z2 is going to be these weights from the previous layer. So there are some weights coming in from here. So they'll be coming from node 1, but this is a different layer. So we will say layer 2, and these will also be like layer 1, right? 1 to this node, right? So maybe 1, 1, and 2, 1, and 3, 1, right? And there's also some data coming in. So weights are the parameters that we will be estimating eventually, but there's also some data coming in. What's that data that's coming out of like the first hidden layer? What is the output? Like don't let's not call it data. What is the output that's coming out of the first layer? Okay, think about this A, right? We did 2. So at every node, just remember there are 2 computations happening. The first is the Z, and the next is the sigmoid, right? So the output of the sigmoid is coming out of this layer now, correct? And so that's what, so instead of X, I can just like write A1 here, right? So Z2 is W2, A1 plus B2 if there is a bias. Okay. So let me just like stop here. So this Z2 will have like, we will have an A2 as well here, which will be like the sigmoid of Z2. Okay. So like, again, like I'm repeating, the only thing that you need to remember is that like in every layer, for every node, we are summing up everything, right? And then next, we are passing it through my activation function, which we are assuming is a sigmoid. So that's the fundamental computation that happens in any neural network. We'll see that we can vary a lot of things. For example, I can change the nodes. Maybe I can change my activation function. Maybe I can do something with my data. I can do something with the connections. But this is the fundamental thing that's going to stay. Just remember that at every node, these are the two important computations that are happening. Okay. So before we move on, and of course, like, because you have done logistic regression already, you already must be having these thoughts that how do we get the weights? And that's the big question for today. And we're going to talk about like forward propagation and then backward propagation. We'll see how the gradients are calculated. But let's not worry too much about it. As long as you understand the basic idea behind how this computational graph works, let's move on, right? So I wanted to show you this perceptron, and now you'll be able to relate to this better because this is like the simplest neural network. Now I try to show you the equations first and then come here because now I think you can relate to it better. And it comprises of like all this is doing is that it has like this data coming in. So this is my input layer, right? And then I have some weights. And notice like even the hidden layer, there's just like one node. That's simple. So it's very much like the logistic regression model, right? It's very similar to the logistic regression model. The only difference being that we don't use like for a standard percent. The activation function that's used is the sign function because we are like trying to predict a plus and a minus, right? So whether you're in this class or this class, not like the probability. It's like a classification type problem. So you have the sign as the activation function. Now we'll try to understand why we don't use sign function as much in like usual neural networks. A lot of issues. One of them I think we pointed out the other day, right? Why we don't use the sign function because of the non-differentiability and other issues. That's one. And then there are other issues as well. But regardless, this is where you like, this is something that you should have in mind because if you just visualize this deep network here that we just saw, right? Just look at it and now think about the perceptron. So this is actually a cascaded perceptron model, right? So you have like multiple perceptrons like stacked together and then also cascaded together, which is why the perceptron is like such an important aspect of like any neural network. All right, so any questions, doubts before we move on? Okay, one thing that must be coming to everybody's mind is like the weight matrix and the dimensions. And one quick way to remember the like, so that the dimensions are definitely going to be really important. The way I like to remember the weight matrix and the dimensions is like the weights are coming into a layer, right? So those are usually the number of rows. And from the layer that they're coming in, those are the number of columns. For example, here, if there are like 3, okay, I should have had like, or maybe let me show you this example. Yeah, so this one. So here there are like 3 inputs, right? So this is like a better picture, I would say, with like 3 input points, and then you have like 4 nodes. So if you think about the weight matrix, right, it is going to be like 4 rows and 3 columns, right? And so here the weight matrix is going to be just like, okay, so 1 row and then 4 columns. So like that, right? So for example, here, this is going to be like 4 by 3. Right, so 4 because it's coming into this layer, like generally speaking. So those are the number of rows. And it's coming from these like 3 input features. So that's the number of columns. So that's like high level how you'll understand, but you will like, once you implement it, you'll understand it better. That's a quick kind of way of thinking about it. But regardless, coming back to the representation of any neural network, and this, by the way, is not a deep network because it just has one hidden layer, right? So these kind of networks are known as shallow networks. But now we will be doing a lot of computation around a shallow network, because if we understand this better, then we will be able to move forward and understand deep networks better. So I think I talked about the notation a little bit. I wanted to talk about the y hat, which I think I mentioned here, A2. So in terms of like the representation, I'll talk about what notation I'll be using. This is a 2-layer. I think I talked about X's, W's. Yeah, I think I discussed most of it. So at every like layer, there will be a Z and an A calculated, and you'll have like a superscript depending on like what is the layer number. And similarly here, you'll have a Z2, A2. Okay, it's so hard to write on this. Cannot believe. Anyways, yeah, so this is about the notation. What else before I forget? Okay, so I think I talked about the dimensions. B, the dimensions of, like, for example, here you'll have a B, so most likely this is going to be more like a 4, 1. Why? Because you'll just have like one B and then all these weights. Usually, this is how we think about this one. And then in the output layer, as I said, weights are going to be, yeah. Any guesses about the dimensions of the weights, the output layer? Like these weights here? Yes. So yeah, so this is going to be 1/4. So, right. So why am I emphasizing so much on the dimensions? Because I figured many of you had issues when implementing logistic regression, understanding the dimensions. So this is how we are thinking about it. And I'll talk about the input, like how we should like save the data and how we should be using that in like when you start coding this. Because on the next homework, you will be implementing your own neural network. Regardless of the packages that are there, I would still ask you to implement one, like a 2-layer network at least. So that's why I'm like focusing too much on the dimension. All right, so moving on. Okay, the computations in a neural network output. So here I just wanted to again like repeat. I know I'm repeating it multiple times. I also know that many students had issues understanding this computation in my other class. And so that's why I'm like repeating it so many times. So Z1 is going to be, of course, W transpose X plus B1, and A1 is just the sigma of Z1, right? So if you just remember this, I think you are good. If you just remember that every node, this is the computation that's happening, I think you are good. Okay. Now, if we go back to this like 4-node network here, and let's say I ask you to implement this, right? And in like by implementation, I mean just like go and do these computations that I just talked about. That's all, right? So when you're doing that, you will have to think about the like how the vectorized thing is going to work, right? So like one way of thinking about it is that you will have like all these Z's calculated here. So you'll have like a Z1, like a Z1 here on node 1. You'll have a Z2 here on node 1, a Z3 here, node 1, and a Z4. Right? So those are the 4 things that you should remember. It's not that there's going to be like a single Z. Like I know maybe I'm repeating myself, but that Z has to be there at every node. Right? So that's that. And then you'll have like the A's as well as at every node. Okay. Anything else before I? All right. So that's fine, I think. I think everybody is okay with that. So for a 2-layer network, so my question here would be like for a 2-layer network, how many equations do you think you need to just like implement this entire thing? For this network, this one. Somebody said 2. Okay, so yeah, I mean, if you're saying 2 set of equations, that's correct, because at every layer I'm doing some kind of like computation. So 2 for every layer, because at every layer you're doing a Z and an A. So and on the next layer, you're going to do a Z and an A, right? So maybe 4 in this case, because you're going to do a Z and an A in this like final node as well, right? So you need these and you need these. Okay, so when you're writing code for implementing this neural network, two-layer neural network, just remember that you need like at least 4 set of equations. Okay, let me summarize if that's like making everybody, maybe write down here. So you will need the first Z1, right? W1 and then X plus D1. And also like, this is actually a good exercise to just like look at these equation one for 1 minute. Sigma Z1, and then you'll have a Z2, U2, and then instead of X, like if you look at the similarity of the Z's here, right? So instead of the X, I'm going to get an A1 here. So maybe I can think of like this X as some like A0, because that's my data, right? And that's B2, and then I'll have like A2 sigma Z2. That's all you need, right? Those 4 equations. But then going here, I know that this is a matrix. So make sure that you know like what are the dimensions. This is like a vector. So know what are the dimensions, because you'll have a Z for every node, right? And then B is, I think, okay. And then A is going to definitely depend on like what are the dimensions of my Z. So yes, that's a 2-layer neural network. Let me see if I talked about everything. Yeah, and then definitely vectorizing these. So instead of like a small case, like a uppercase, as I said, because it's not just one Z, but like multiple. Okay, so this was about like how to make the, like how to do the computations in a 2-layer neural network, right? Okay, so now let's focus on like this thing, the activation function. And we've been using, yes. Yeah, so that's what I said. Like if I'm going to like vectorize this, right? So I'm going to have like multiple, let me go back here. That's a good question. So notice like this Z subscript 1 actually means that it has like all these components like Z11, Z21, Z31, and Z41. Does that make sense? Yeah, so yeah, that's why I know, because this issue is going to come up. In my experience, I've seen when you start implementing it, which is why I'm repeating the dimension thing again and again. Okay. All right. And other thing is that like all of this that we have talked about is about is related to just one input example. So now think that when you're doing this computation and you're writing the code, you will have to like vectorize these equations, and you'll have to vectorize like across the data set. Why? Because you will have like these n examples, right? So the size of your data set. So that's going to come in, and these equations were just like for x1, x2, x3. Basically, these were for xith example, right? So if this was the first example, then you'll have the second, the third, fourth, and so on. So that's why like maybe vectorizing them is a good idea. So think about like how the input is going to come in. Maybe like if we think about the input as like all these examples, like every x1, x2 as these column vectors, like this, then that will have like the rest of the dimensions fall in line. Okay, so again, this is like from the perspective of implementation. As long as you understand, it's like really simple, but when you actually start implementing it, you're going to see like it's not that simple, right? So of course, as long as you understand this 2-layer network, as long as you know that at every node, these are the only 2 computations that are happening, I think you should be fine. And make sure that you are okay with the dimensions of the data and the nodes and everything. All right. Other questions, doubts? Yes. Yes. So like whatever notation I use, if you go and like check the dimensions, this is going to work in that sense. Yeah. So of course, there is no restriction that you have to use it as a column vector, but the way I'm writing the equations, this is what I'm assuming, you can flip them. That's not like a restriction or anything. Yeah. But like I think again, like remembering that all these equations are for like one data point, and then you have to repeat it for like all of them. Other questions, doubts? Okay, I'm pretty sure you're going to come up with doubts when you implement it. I have seen that, so that's fine. All right, so coming to activation functions, and until now, like we have used the sigmoid as like the activation function, but that's not the only choice for an activation function. So one way of like thinking about any activation function is, if you go back to logistic regression, the way we were making our like weights update is based on the gradient, because in most of the situations, most of the problems, we assume that the error is like that convex surface, right? And if there is convexity, you need to have like you need to like differentiate your you need to find the gradients basically, right? And so differentiability is important. And from that perspective, we don't like the sign or the identity, but we like sigmoid, right? So now sign, as I said, and sign, as I said, like non-differentiability prevents its use for creating the loss function at training time, especially with large networks. So it becomes an issue because it's not like smooth, right? So it's non-differentiable. Now, sigmoid is good because it's useful for computations that are interpreted as probabilities, as we saw. And for example, this is easy. This is like sine z. This is how I write the output. In this case, it was 1 over 1 plus e to the minus z, right? And then there is this third one, which is the tan h activation function, and you'll be using this going forward. So the way this is like represented is like e to the minus z minus 1. I think it's 2z and e to the 2z plus 1. You can go and check if I'm wrong, might be the case, but this is preferred over sigmoid, like when the outputs of the computation are desired both to be positive and negative. So what is it that makes it like so good, right? So like if you look at the sigmoid, and it was more like an S, right? And so this was like 1, and this is like the 0, right? And it's like an S. Okay, I'm really bad at drawing. Basically, what I'm trying to say is like an S-shaped curve within 0 and 1. But this like tan is going to go from like +1 up to -1, like something like this, right? So if you have like two different classes, it's easier to kind of spread into that area. And like the paper, the reading for today actually talks about like why this is better. But this here is only like an introduction to different types of activation functions, right? So tan H is one of them, which we haven't seen before. And you can think of like tan H as like more of an elongated sigmoid. Yeah, that's what it looks like. It's, except that like it's ranging from, this one ranges from 0 to 1, that is from +1 to -1. So another popular one is the rectified linear unit, or the ReLU. And we will again be using this a lot, especially with neural networks, right? So these are like both of them, this rectified linear unit and hard tan H, they're popular because they are very easily trained, and the gradient descent converges really well if you're using them, as opposed to the sigmoid or the tan H, especially the tan H that like slows down your convergence, as you'll see. But regardless, I'll still make you implement it. So yeah, but like when you go and like try to improvise on the timing and other things, then ReLU and the leaky ReLU actually comes in. So I haven't introduced that here, but ReLU is something like this. It's like you're trying to find a max of, I think, 0 and z. So it's more like this. So this is like linear here, and it's like 0 if the value is negative. Like it just like goes to 0 after that. So you will see why this is and how this is useful when we actually implement our network. But for now, I just wanted to introduce that there are different activation functions that are available, and ReLU is one of the most popular choice. Why is it a popular choice? We are going to see that going forward. All right. So that was about different types of activation functions. Let me see if I missed anything before we move on. Yeah, I think we are good. So let's keep going. And if there are questions, just like feel free to stop at any time. Okay, so here's the thing now. Like we understood what computation we are doing in our graph, and we are finally getting the estimate, which is my loss, right? And which is cost based on like all the average of the data, right? But why are we doing all of that? Well, we are doing all of that in order to get the best parameters, the best weights that give me the minimum cost or the minimum loss, right? And in order to do that, gradient overview of like what, like how gradient descent works. But then we'll go into the forward propagation and the backward propagation, because backward propagation is the way wherein we get the gradients. So for now, we're just assuming that we know how to get the gradients for all the weights. And these are the steps, right? So just like bear with me, because I know that back propagation is going to take some time, like just understanding it. And through back propagation, we get the gradients. For now, just imagine that we know how to calculate the gradients. Okay. So how gradient descent works is that you have like some input data and you have a cost function, right? So I have like input data, and then you calculated the cost function. And cost function, if you remember, is going to be like a function. And this is for the two-layer neural network only. Just like I'm assuming that this is the two-layer network. So this is going to be a function of the weights, right? The bias in the first layer, weights and bias in the second layer, right? And I can like, I just need to average these. So eventually I'm going to get some like 1 by m, if m were the number of, and then I'm going to sum them up. A2, now with the new notation, it's not y hat, but A2 and my y. Right? This is how we were doing, right? And now we need to get these parameters, right? These were the parameters that need to be like the best ones to get like the best loss, because I'm like minimizing based on some values. So again, the way we did it in logistic regression, it's exactly the same, except that the parameter updates are going to be more complex. So let me like write down the steps. Maybe let me write down on the next slide, right? So I'll just like write down step 1, initialize parameters. And we'll see why we do not initialize these weights to 0. I'll talk about that. But just remember, unlike logistic regression, we don't do that here, right? So we initialize them like random. And there is a reason for that I'm going to show you. But for now, just remember, not 0. Okay, and then second, just like repeat these steps, just like we did in logistic regression. So do some like predictions for all the data, right? So let's say I have like y hat for some ith value, and let's say I have computed it for all 1 to m. Let's say that. And then I need to have the gradients for the for both the weights. So dw1, which is dl w1, and db1, which is dl db1. And similar to this, I also need my dw2 and db2, right? So I'm just like assuming that I have these, and this is how they will be calculated, right? These are the gradients that I'll be calculating. How I'll be calculating, we are coming to that. And then eventually the third is you'll have the update rule, which is for each of the weights. And let me just write it for W1 and B1 only. And then you know how to do that for the second set of weights. So again, similar to what we had, minus the eta, which was the learning rate. And then B1 minus eta dB1. Okay, so this is just like this is like one iteration. Obviously, you'll be doing that for like the multiple times, and then you will also do it for the second ones. And that's it. Right? So now, why I decided to write all these is because if you think about the way you implemented gradient descent, it's pretty much the same, right? Now, the question arises, it's of course pretty much the same, but it's not the same in terms of like the weights that we had. Now we had this like huge matrix of weights, and we also have like these extra layers in between. It's not just like I got the loss, I calculated the gradients, I updated the weights. It's not like that anymore, because you have like these different set of weights and these different computations that are taking you further and further, right? And so you have to come up with some good, like I would say, algorithm or some way of getting these DWs and these DBs right? Because they have to be based off of like how you did the computations to eventually get this L, right? Because the gradients will be like, so what exactly do we do in logistic regression? Well, I'm calculating the gradient of this L with respect to the weights I'm supposed to estimate. Right? So the way to do that is something that's known as back propagation, right? But before we jump into the math of back propagation and forward propagation, I quickly wanted to talk about the initialization of weights. So let's do that, and then I'll talk about the entire process of like how do we do that. So as I said, we in this like step saw that initializing parameters should not be exactly equal to 0, right? And the reason being that let's say you have like this two nodes, right? So let's say you have like some kind of a weight that it's just like two nodes, let's say, and two inputs. And then you have this like weight vector and you said, okay, everything is going to be 0, right? And when you do the computations like the Z's and the A's, right? Everything like, okay, so basically this is what's happening. X1, X2, here, 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 right? So everything that's computed here and everything that's computed here is going to be the same because I have everything like 0, right? And so what actually happens is that like when I'm going to calculate the gradient of these, right? That's also going to be like similar for like every, so basically when and I'm calling dW as like dl, dW, right? It's going to be something like u, v, and like the same rows at every like node, right? When I calculate the gradients. So these gradients are important because I'm making the update based on these gradients to the weights. So the updates is again going to be same. So the issue that happens if you initialize everything with a 0 is this like symmetry gradient problem, right? So symmetry gradient problem, which is why we don't want to do this. In logistic regression, it worked because I'm just doing one single, like just imagine that was just like a single computation. So it was just like everything going into this node and then everything. So okay, I don't have other nodes in my like set of weights. All right. So now what's the way of like getting out of this, right? So when you will be implementing your own network, just make sure that you like initialize it randomly. And also like not going beyond a certain like value. So not having them too big, not having them too small. So now the question arises, what is like too big and what is too small? Like generally speaking, if you're using like NumPy and you're using this random.randn, right? And let's say like I have this thing, you usually like it's okay for most of the problems to have like a value equal to 0.00. It's okay to start with that, but of course you'll have to do some tuning there. Maybe it might not work well for your data. So that's a good place to start, like experimentally and empirically speaking, right? So initialize randomly, make this like not too big. And one reason why we don't want to make it like extremely big is because of the way the sigmoid is, right? So there are those saturation regions in your sigmoid, right? This is my saturation region and this is my saturation region. And if I have like two big weights, they might quickly start lying in that region. And so like your class, I really want everything to like lie somewhere in this region, right? So then that is an issue as far as like your problem is concerned. So make sure that whenever you're initializing, that's something. Okay, so this is just like one aspect of something that's known as hyperparameter tuning. So this is like one hyperparameter. I'll keep talking about it like throughout, but this is like just one of them, that the initialization isn't under your control, and this is how you should be initializing, right? There are other hyperparameters like how many nodes, how many layers, and so on, and what should be the value of eta and other things, but we'll talk about each one of them as we encounter them going forward. Okay, so that was that. And what else? I think I already discussed deep networks. Okay, so it's about like a two-layered neural network. How do we do the computation? How do we get the final output, which is the loss, right? And then how the gradient descent works. All of that is good. And maybe to a certain extent, we have an idea of like how the data flows from the input to the output, right? So there is a specific term for these computations that we just talked about, and that's known as the forward propagation. So whatever we've been doing, if you think about it, right, intuitively, the idea is that I have some input data, right? I did some computations and I eventually got some loss or my cost, right? And the way this is like working is that I'm feeding all that information forward. So these are also known as like feed forward networks. So if you come across that term, that is nothing to be confused about. It's a deep neural network and with a forward propagation working, right? So for any so I would like to write these generic equations for a forward propagation because these are going to help me understand backward propagation. And we'll see what backward propagation is and why is it so important. Okay, so let's say for in forward propagation for a deep network, meaning that I have more than 2 layers, like roughly speaking, more than 2 layers is a deep network, right? How does the forward propagation work? Well, the way I like to in general write it down is that for any layer L, right? For any layer L, you have like these things that you need to figure out, right? WLA L minus 1 plus BL, right? And you have this AL, which is the sigmoid of ZL. But now that we know like these many other activation functions, I'm going to like be more generic and just call it like G of ZL, right? So this here summarizes forward propagation for any layer L, right? And here, like if you look at this equation, I have like this AL minus 1, but remember like when we started computing Z, we had something like this, right? So for the very first layer, just like think of this as like A0. So my X essentially is nothing but like this A0, right? So the overall algorithm of forward propagation and backward propagation in conjunction with the gradient descent is essentially used to get the optimal weights, right? So let me just like summarize this. So you'll have forward propagation with the data, right? And then you'll compute the gradients using backward propagation. So that's another algorithm that's used in order to get the gradients. Now you have seen, like I would say a flavor of that, not quite, but like when you were calculating the gradients in logistic regression. Let me quickly show you what I mean. Because again, that is going to help you understand how this works in a deep network, right? So remember this logistic regression. Again, let me just go here. X3, right? And then you had like ZW transpose X plus D, and then activated sigma Z, right? And then you had L A Y. A is like the Y hat that we had. Okay. So what we did, like we remember the equations that you used to implement your gradient descent. So you had like basically what you're doing here is that you wanted to calculate the derivative of this with respect to like we need to calculate the gradients with respect to all the parameters. But basically what we want is something like this, like dl of dw, dl db, right? This is what we wanted. But what we actually started doing was that we calculated dl with respect to dA because there is no direct relationship between the weights and the bias. So if you think about it, that's what we did here. So DL, DA is like, and of course you can do that. So I'm like talking about logistic regression. So it's the cross entropy equation, the log 1 minus y log A plus 1 minus y log 1 minus A. So if you just like go and differentiate it, this is what you're going to get. And I'm not going to like go over that because I'm pretty sure everybody can do that. So using that, what I'm going to do is here in this like part, in some ways I'm back propagating this calculation. Of course, we don't see that in a logistic regression model because we don't need to see anything. It's just like one step, right? But actually we're using this calculation to actually compute this DL with respect to DA at this point. And then eventually we need to compute here something which will lead us to this. So basically DL dz, and then using this we can compute this, right? So for example, for this like dl with respect to dz, is going to be the partial derivatives. So we use partial derivatives for every step is going to be L, Z. So basically applying the chain rule, right? And eventually using that, I'm going to get this dl dw because that's going to be dl dz times like just differentiate that. Right. So what I'm trying to like emphasize here is that even in logistic regression, we were doing something like this, right? What we were doing was like I started calculating the gradient of the loss with respect to like whatever parameter I had, which was y hat, and then utilize that to compute the gradient with respect to my a, and then kept going backward, right? And we already had those equations, so I'm not like deriving them again and again. But the fundamental thing that I want to like show you, and let me make these shorter. So like from now on, if I'm using dl with respect to dz, I'm just like, I will call it dz and I'll call it dA so that like these are not tedious, dB, right? So let's say we are denoting them by these. And what actually happens is that this dz at every point is going to be dA times the first derivative of this with respect to z. And g, by the way, is the sigma. So this is the first thing that you're going to get, which is going to stay with us, of course. And then the important thing that we need to do is dw, which is going to be dz times x. You can see that here. You can just look at that equation, like z w transpose x, that's what this is going to give. And dB, by the way, is just going to be dz. Okay, so these three equations are going to be the heart of your backpropagation algorithm, because actually for any multilinear network, neural network, this is what we are doing at every node. Just like with forward propagation, we had those two equations, remember, the z and the a. In the backward propagation, we have like these three, rather I would say four, maybe because dA sometimes is important, but I would still like focus on like dw and dB using this like dz. So this is all that is that's all that is there to backpropagation. You're just calculating the derivatives with respect to every parameter. The only thing that changes is that you like in the chain rule you might add another partial derivative, because as you're like further away from the source, you'll have to multiply another like partial derivative, right? So let me again show you with like using like a two-layer network so that the things become clear what exactly you need to do. One thing that you should remember, like when you're implementing this, is that once you know the dimensions of the weights and the bias in your forward feed, those dimensions stay the same in your backward feed as well. So basically saying that if you know the dimensions of your W for like layer one, obviously you will be like calculating the derivatives for that W1, right? So the dimensions of both of them are going to be same. So that's why I'm talking about like I'm saying partial derivatives, because those are the components of that big matrix of derivatives. Okay. All right. So again, because we understand this part for a single node, like what happens when I have two nodes, right? Because what actually is happening if we go here is that I have some like loss here, and I start calculating the derivative with respect to my immediate, like whatever unknown parameter is there. So for example, dl with respect to dA, using that, I go to this layer, right? And then I compute some other like derivatives. So essentially for every connection, I need these dWs and dBs, which is dl with respect to dW, dl with respect to dB. And so that's why this is known as back propagation. Why? Because I'm propagating this information from the right and then taking it back. And also, in addition to that, like, why do we need these? Anybody remembers, like, why are we doing so much to get those gradients? Exactly, right? So that's why we need them. The only added complexity here, like added to the logistic regression part, is that I have more than one layer. Like with one layer, it would have been like just like once and done. But here I have more than one layer, so I have to do this like propagation, so to say, of these gradients throughout. Okay? So that's what this is, and this is how, like, this is the most fundamental algorithm to estimate deep neural networks, known as backpropagation. And both forward propagation and back propagation work in conjunction with one another. Okay, so let's try and understand the same thing using like two different nodes. Like how do we propagate using two different nodes? And I think I've been talking a lot and I can see people tired. So let's take a 5 minutes break and then come back with the and talk about like this two layer thing. And like whoever is interested more in the math side of like how we derive all of this, I have a video on my YouTube channel, like that is from the other course that I teach. And there, like I actually derive everything. So just in case, like if you're interested in the math side, you can go and watch. Like the playlist is called Machine Learning from Data. So you can check like back propagation. All right, let's get started again. So as I said, like when we are using the gradient descent to estimate the parameters like the weights, what we're doing is like first we forward propagate and then we do the backward propagation, because using the backward propagation, what I'm doing is I'm calculating the gradients of the loss with respect to all the parameters that I need to estimate. And then I'm making the update in my gradient descent, right? So I just wanted to show you how this is going to work in a two-layer network. So let's say these are my inputs. So some X and then, okay, I'm just like skipping a lot of, because I already, I think, wrote that multiple times. But I just want to show you how this is going to work in like more than one layer. Okay, can I erase this for, okay. Right, so this is the first thing that happens, and then the activation. Let's just write it A1 because it could be any activation, so I'm not like going into that. And then you'll have another node, right, which will have like Z2, W2, and then this is A1 plus B1, and then of course A2, and then you'll have the loss, which is like a function of A2 and my Y, right? So now the way I'm going to backpropagate is similar to what we did in logistic regression, right? I'm going to calculate like this DL with respect to DA2, right? Because that's what's known to me. So that's what backpropagation means. I'm going to calculate, like, let me just like write it down, DA2 here, DZ2 here, DA1 here, all that, like these are the derivatives of the loss with respect to these parameters. But now I'm interested only actually in the W's and the B's. But I need these because like my weights pass through these, right? So like that's high level, that's what's happening. And using this, I will be calculating dz of 1, right? So in the forward propagation, if you think about it, for any layer like L, right, in the forward prop, like the input was some like a L minus 1 for the L, like any LS layer, and the output was a L ZL, right? This was like, this is what was happening in the forward propagation. But now in the backward propagation, I'm just like going to erase this. The input is my DL, okay. This is my input actually, right? DL with respect to DA2. So I'm going to calculate the differential of the loss with respect to this like DA2, right? And once I have that, right, I'm going to use that to compute this, because like this here is going to be DL with respect to DZ2, right? And here we usually apply the chain rule, which is DL, DA, DA, DZ. So basically what I need to do here is that somehow I should be computing this. And for that, I should compute this and this first. So this is how this works. So that's why we call it like backprop, because I'm like using all these gradients to compute this thing here. And why is this important? Well, this is important because remember, in addition to all of this, there are some weights and bias that need to be like, so this is like W2, B2, right? And then there are some like W1, B1 that need to be computed, right? And so once I have like this, like all this information here, I will eventually get my DW2 and my DB2. And once I have that information, I can make the update to my weights. So this is why this is back propagation, right? And so once I have like this information, I can calculate this, right? And so like, for example, eventually when we calculate any of these z's, like the derivative of the z, whether it's like in layer 1, in layer 2, we get this generic equation that I'm going to write down. So as I said, you can go back and check whether this equation matches or not, but this is the generic equation that you should remember. And maybe like, let me write it down here. So there are these like 4, I think, equations that again you should remember when you're implementing. So I know that you will be like implementing it yourself. Is W2 DZ2, and then an element wise, because these are vectors and matrices, so this is an element wise multiplication. with the derivative. So this is like saying this is the first derivative and then z1, right? So this is the equation that is going to be there for every z. So for example, if this was dz2, then these are going to change accordingly, right? So this is what's going to be for dz1. Let me write it down for what is going to be dw1. So this is going to be dz1 times x, and db1 is going to be just dz1. And I would like recommend everybody to just like go and check whether this works, like whether these equations are right or not. So in general, if like I'm writing it for any L, right? If I'm writing it for any layer L, I need 4 things to come in. There's like a DAL as well, right? So DA1 is WL times DZL, right? So these are the only 4 equations that actually you'll be computing when you're calculating the gradients in every layer. And these are the gradients that you're passing because eventually you need this and this to make your update in your gradient descent, right? This equation here is like specifically important because just look at it, right? The gradient of that z, the summation that we do, is actually dependent on the weights in the previous layer times the gradient of the previous layer, and then an element-wise multiplication with the first derivative of this layer itself. Right? So these have already been derived, and in this like course, I'm not asking you to derive them. If it was the other one, I would ask you to derive them. But regardless, I wanted to show these, and if you're interested, you can go and like check if these are correct or not. But you will need these 4 equations when you're implementing your own neural network. Okay, and as we'll read the research paper that we're looking at today, you will see that this falls in line with that as well. So these are like well-known equations, and for any layer L, let me write them down so that like we have everything clear, is that we have like a d is d of L. So as long as you can implement these 4 equations, I think you're good. Will be dA L element-wise multiplication. So this is like a G L first derivative. Why? Because this could be a sigmoid or anything that's L, and then dWL equals dCL. Okay, a lot of confusion. And then dB. This is easy. This is just like dZ of L. And then finally we have like dA of L minus 1 equals WL times dZL. And just like going in and checking whether this like is correct or not would be some like a good exercise to just like do. All right, so any like questions, doubts about anything before we move on? Yes. Okay, which one? This one? Here? Yeah, so this is the first derivative. So this is like okay, so this G could be, let's say, sigma. This could be sigmoid. And so you're going to differentiate that, right? So that's the first derivative. Yeah, the small line up there, that's what it is. Other questions, doubts? Okay, so that's all that's there to back propagation. I've like summarized that. So this is how this entire thing is going to work. You have some data and you need to estimate the model parameters and get the best ones so that you can predict something with them, right? And so what you'll do is step 1, you will do forward propagation. Remember the node computations that we did? So you're going to do them for all of the nodes and all of the layers, right? And then next, once you're done with that, you're in the output layer. You will compute the partial derivative of the loss with respect to whatever your A was, right? And then you'll propagate the information from the output layer to the input layers because you will be estimating or updating the weights in every like previous layer. right? So that's what this is saying. Compute the partial derivatives of the cost function with respect to all of the parameters that feed into the output layer, right? And then go back one layer, go to like, if this was L, go to L minus one, again, compute the partial derivative. So this is actually telling you what we did here, right? So do this dA, right? Once you have dA, you'll have to compute dz. dz is like dl with respect to dz, but there is no like direct relationship between z and l. So you will have to establish that relationship using this a. Similarly, like next, we need to update these w's and these b's, right? But again, there is no direct relationship between L and B and W, just like in logistic regression. So I can use these Z and A to get to there, and so on. So that's why this is like back propagation. Okay. So as long as you understand the fundamental idea of like why we are doing this and how this is happening, you might not go into the details of like how this is derived. So that's why I don't cover that in this course, like how to derive this. But if you're still interested, I can point you to resources. I can point you to my own video where you can see how we derive them. For like implementation purposes, it's absolutely fine if you know these four equations and you use them to implement your model. Okay, so that's what this is talking about. Compute the partial derivative of the output for the current layer. Compute the partial derivative of the cost function with respect to all of the parameters that feed into the current layer. So we saw like what are the parameters Z, A, W, B, right? And then keep repeating the steps. Well, this is like subject to discussion. How many times do we repeat? What all layers do we need and other things? But this is like high level how a neural network works, right? So that's it in this, but I wanted to go over the paper that I have. Let me just, how do I stop? Yeah, I'm going to upload the slides just in case, like when you're implementing and you want to see, okay, share screen. If you want to see these like four equations and like when you want to implement. So I'm going to share this as well, but let's go back to the lecture. Okay. I have this paper that I want everybody to go over. And so what I demonstrated was a very basic back propagation algorithm, just like for two nodes. But now you can imagine that this is like a fully connected neural network, like a deep network. So then like how can we like implement back propagation? So why is this important? This is important because if you just look at this network itself, like this one here, or even like this one. Now, we just talked about, okay, this is what happens if this node was connected to this node and I'm going to do some back propagation here. And then I'm going to estimate these things here, right? But then when you're looking at this one, right, just imagine just like for one example, imagine the amount of computation you are doing. Like I have a data point, right? I did all the computations here and then I calculated the loss. And then I went back and did all the gradient calculations and all those big matrices. And then eventually I got some final W for one example. And then I ran that for like maybe 1 million examples in my data. And so like the way like efficiency wise, this is bad, as you can tell, right? Because I'm doing so many computations just for like getting that one W. And so I need something to improve this algorithm, to make it efficient, to make it like work better, right? One like very common problem, like another problem that you might just like looking at it tell, that this is a complex model that you're trying to fit to your data, right? And the more the complex model is, like remember from our discussion from bias variance trade-off. So here, this is a complex model. The tendency is what? Like what can happen from our knowledge of like bias and variance? Yes. Exactly. So first, like interpretability wise, it's bad, right? I cannot interpret. If somebody asks me, just go and tell me what's happening in this node, it's totally out of my control, right? Once I just like implement it. So it's difficult to explain to somebody why I got this result versus that, which was, as you can tell, easier in decision trees. I can just say, okay, I'm splitting at this point, and that's why this data point lies here. And so that's why I'm predicting this. But it's hard to tell for this one. Let's say I'm predicting breast cancer, right? So if a new patient comes in, it's hard to tell why I predicted that this person has a high risk. Like, can I tell from the parameters? Well, actually, no, I cannot really say that. So those are some of the issues that are there. Plus, there is this issue of overfitting. So it's a complex model. It's going to fit. So what happens actually, and you will see that when you start training your network, initially it goes like really, it has a huge bias. So it is like predicting bad. But then as you feed more and more data, it starts to come closer to your actual values. And so much so that like it comes really close and the accuracy is pretty high on the training set, which means that it has like overfitted in some ways. Right, so overfitting is another issue, which is why we have to address those issues when we are trying to have like an efficient model. And this is an excellent paper that actually talks about like what all issues this entire back propagation and forward propagation actually poses, and how can we deal with those, right? Okay, so this is talking about that. And so the first section talks about learning and generalization. Always remember, if your model is giving you like 99.99% accuracy on the training data, that's bad because most likely it's not going to generalize on the unseen data, right? So generalization is a problem because of overfitting with neural networks, right? So there are many approaches. I'm not going to go into this part because I have a whole lecture dedicated to how to deal with that, how to deal with overfitting, how to regularize our models. But still, like going over this quickly would make sense before that lecture. So this section talks about like how we can like what generalization means. I think like everybody understands what it means, like how well this model works with some unknown test data or like data that's new, right? And then this talks about standard backpropagation that we just saw, right? So I'm going to show you the four important equations that are like required, or like they've come down to three. So basically this is like our, I think Z, what were we calling this? And the other one is this A. Yeah. So eventually when we come to the one with the element wise, yeah, this one, this is the DZ1. So this is just like showing you how we can apply the chain rule, and okay, everybody's able to see that, right? So this is just like showing you what we just talked about in the slides, right? So this section just talks about the basic standard backpropagation. So we understand that, except that this is like a different notation, but eventually this is telling us this is how we make the updates, right? So this is that, and here is the gradient descent update, right? And this section 4 is like really worth reading. And I would ask everybody to go and check this, especially before you implement like this back propagation yourself. Okay, so this is something that we understand well, stochastic versus batch training, and how both of them work. The same rule applies here, the one that we discussed and implemented in logistic regression, right? So you can have both, right? Now think about what happens with batch learning in this one. It is going to be extremely slow. You're just like for one update running the entire data and then getting the final maybe average of the weights, or like, I don't know, some max of the weights, or something like that, right? So that's how the batch is going to work. But so of course, like stochastic is a good option here, because for one data point, I'm making the updates no matter what. And then I'm getting the second one and then making the updates and so on, right? So there are advantages of stochastic gradient descent, much faster. You can tell why, right? And also sometimes it is able to get the like good results, because like some people might argue that we can go away from the results given the non-linearity that's there in the model. But in most practical situations, we get good results. So that's the good thing about. So these highlighted things, they actually tell us that these are the advantages of stochastic gradient descent. That's one. And then there are some advantages of batch learning as well. It might be able to find like better results, like in terms of accuracy. Maybe it's slow. I understand it's inefficient, but maybe we can come closer to the actual value. But then this has like, I would say still like a hidden bad thing about it, that I actually fitted the entire data. So like how good that model is subject to discussion, right? So yeah, but of course, like it converges well, right? And then many of the acceleration techniques, we saw momentum and other acceleration techniques, they work well with batch learning. But I would say that like we have ways to implement that with stochastic like gradient descent, like stochastic learning as well. So I don't totally agree with this, but yeah, that's there. Okay, so next. Yeah, sometimes this is a good thing to do. So like shuffling the examples and not like sequentially feeding them. So choosing the examples with maximum information content. And the best way to do that is to randomly pick rather than like sequentially picking your data sometimes helps, especially with neural networks. So shuffle the training set so that like successive training examples like really belong to the same class so that you have a good representative like data, right? And then present input examples that produce a large error more frequently than examples that produce a small error, because then you're not making like much updates to that, like your gradient is going to be very small then, right? And then you're not making like quick updates, like intuitively speaking. So that's why this is important. Normalizing the input, I think this applies to like any algorithm, so not just neural networks. So this is also an important consideration. Transforming, I need to think. Yeah, so this section actually talks about the activation functions. What are like activation functions that are used? Non-linear activation functions give neural network their non-linear capabilities, as we can tell, right? And one of the most common activation function is the sigmoid monotonically increasing function. We've seen that, right? And then the most common one is this. So we use this for a logistic regression one, right? The other one is the tan-h. And of course, you'll be implementing the tan-h this time. Sigmoids are symmetric about the origin. We know that. And sometimes the issue with sigmoids is that of saturation, right? So that happens. And especially if you think about like I don't know how to say that. If there is like a data point that lies somewhere, like let's say that's a binary classification problem and you have a clear boundary, but then there is a point that lies somewhere like on the boundary. And so sometimes with those kind of examples, it does like sigmoid doesn't really work as well, right? So the solution for that is like tan-h, like one solution is tan-h. And even a recommended one is like this I would say, approximate tan-h, right? So these values have been computed after like doing a lot of experimentation. So this converges really well, this updated tan-h. This is just like an experimental value if you look at it, like some constant times this, right? So these are like some of the important, I would say, activation functions. Another one that has been used quite a lot is this tan-h plus some constant value. And just I would like leave it to you to think about why this is sometimes helpful if we add a linear term to your activation function. How could this be helpful? And think in terms of like we are calculating the gradients and updating the weights. How can this be, like in what situations can this be helpful? Okay, think about it, that's fine. Okay, so here's a better picture of tan-h versus the sigmoid versus the one that I was drawing that was like really bad. So this is the standard logistic regression sigmoid that we were using, right? This is the tan-h, and I would say here they have they have this approximate version of tan-h, but it is more like the sigmoid, like flatter here and more flatter here. So even this picture is actually telling us that there is a rapid like change here and here, like on the curves, you can see, right? If we add this like linear term, or like if we add this thing, sorry, not the linear term, if we add this and then change a little bit here. So that's actually telling you something about the gradient when we do the calculation. Also telling you about the output that you're going to get out of that. Yes. Yes, that's right. Yeah. So that's why, like, just go and read this normalization section. It's going to talk about like how that like it's related to the. Okay, so that's that. And choosing target values, I wouldn't touch this part because I want to talk about this in later lectures. Let me just skip it for now. We talked about initializing the weights, right? So we talked about why we need to initialize because the symmetry issue comes in. Yes. You can access the link. I can download it and upload it on Submiti. Oh, okay, okay. Okay, I thought I picked it from Google Scholar, but maybe I got this link from somewhere else. Okay. If you cannot find it on Google Scholar, like whether you find it or not, I'm going to upload it. I'll upload it. I wasn't aware that because I just Googled the name of the paper. I know that this is like a very good one when, especially when you're like implementing things. Okay, so that's that. Okay, so here, this is something that we haven't talked about. This paper also talks about like some of these algorithms that we discussed earlier with logistic regression, for example, like the momentum and like how can we, like what learning rates should we use? Remember in the gradient descent, that question came up earlier, right? What should be a good value of eta? And then we were just like picking up any 0.01. But that question is like even more important with neural networks because just imagine the amount of updates we're doing, right? So like, okay, you can keep a fixed learning rate, that's fine, but sometimes like that can pose issues with convergence, right? So we usually what we like to do is that use adaptive learning rates depending on like how far we are from the minimum, and based on that like we decide how like what steps to take. So for example, intuitively think about it, if I'm like really far away from the minimum, then I'm taking like bigger steps. But as I'm coming closer and closer to the minimum, I start to take smaller steps. So that's what like this thing means, adaptive learning rate. So this is something that I'm not asking you to implement right now because we need to understand better like how to pick this. But this section actually talks about like how we can go about that. But again, we are going to discuss that in some of the later lectures. And this paper is something that we're going to look at again. Like there are some very good, I would say, explanations of the convergence of the gradient descent. So if you're interested, you can go and read it yourself. Otherwise, I'm going to like come back to this one in some of the later lectures. All right. So yeah, this is actually showing you what I was saying, right? So if we select an eta that's like really big, so then notice what's happening. Like let's say this is my error curve and I have like a very big eta. So this is what's going to happen. I'm like, it's really hard to come down here, right? And if I choose a very small one, then it can take like forever to come down, right? So for it to converge. And so there are ways to deal with that. There are ways to come up with some like some middle value. And a better like way is that like when you start bigger, like take bigger steps. But as you're like coming closer to the minima, then you start taking smaller steps. So again, right now it's okay if you don't understand that. I'm not asking you to do all of that. As long as you understand forward propagation and backward propagation and the 4 equations that are required for backdrop, I think you should be okay for this week. Next, like the next lecture is going to be about how to regularize, how to deal with overfitting, and like other issues that are there with neural networks. So that's what we're going to cover next time. So I think that's all for today's lecture that I had planned. If there is anything else anyone want to comment or okay, so there is a okay about the homeworks. I think that question came up, so let me just answer that now. There is a homework that is due this Friday, but like starting from Friday, there will be a homework due every 2 weeks and not every week because the homeworks are going to get bigger, not harder. I wouldn't say that they're going to get harder. It's going to be like same difficulty level, but yeah, you'll have like 2 weeks starting from this Friday. Okay, so that's all. Thank you. Yes. Yeah, that's fine. That should be okay.